All right, guys, let's get back into it. So we were looking at this article about Pratt parsing, and we had kind of made it to this section, barring a little bit of trouble with my recording. This is where we made it to. So let's add all kind of weird expressions to show the power and flexibility of the algorithm. Let's first add a high priority right associative function composition operator. So I suppose we could do that. But I'm not sure how interesting it is. There's also this this kind of this kind of expression doesn't really make any sense. What does it mean that you multiply this function composition by 3 and then by 4? But something else we can do that's kind of equivalent. I have the code here. Why don't we add another operation? For example, there's division, and we can also add exponentiation. So the slash, that's this. If we want to print it, we'll just go through the code and add all the things that we need. So now we can print it. The token thing doesn't change. Let's go ahead and get the tokenizer, or the lexer rather. And why don't we put that? Why don't we put it up here? Because it kind of like makes sense that it comes here right after we define the token. So this should all be the same, but maybe here where we say token from substring, that has to do some other stuff. So we can check on the slash, then it's a slash, and if it's this thing, it becomes the carré. So that's quite simple. Now let's look at the expression. Printing the expression doesn't change. dInit doesn't change. Print token doesn't change. Why do we have print token? Well, okay, it's to print atoms. Passing a number is still the same. Let me just check something. All right, so we don't even support function, or rather identifiers, but that's all right. Now we have this thing. So I think maybe these should all have a precedence that we would like to define here. And actually, we can just like put them in the order that they should have, of the precedence they should have. So something like this could just be what we do. So really we can just return this, I think. Let's see if this basic parsing still works. So it doesn't work. Yeah. So I think we can go ahead and say that this should be backed by a U8. And then if we try to run it, that also did not work. But there should be a way to convert it. So we can go ahead, and I pulled up the documentation here, so we can look at enums and int from enum. Okay, let's try that. So add int from enum, and we can run it, compiles, and it does pass the right thing. So let's try with a different kind of expression. So for example, we can say divide by 5 times 6 and the carry for 7. So it should be rather complicated, but let's see. So the division happens first, the carry happens before multiplication, and so I think everything is correct. So if we go back to the article, he basically had to add one line, which I guess is fine. It's not really strongly typed or anything, right? It's just a character. We also added one line, but it is strongly typed. So I think our solution is better. And this thing that he's doing, it won't scale to a real programming language, I think. But it's just for learning, so it's fine. All right, so it's a single line. Note how the left side of the operator binds tighter, which gives us the desired right associativity. So we don't, okay, so one thing we don't really have is the option to change associativity, right? Which might actually not be great, because if we have something, I'm just going to keep this, if we have something like this, what should that equal? Because I think, well, let's say like this. What should this equal? Because if it's 2, 2, 2, 3, that's equal to 4 times 4, that's 16 times 4, it is actually 64. And this thing is 2 to the 8, which is also this. So you can see it's different depending on how we do it. So let's see what happens. And unexpected character in the number. And why does it say that? What exactly is the character? Why don't we put that here? Like that. So here we go. Unexpected character in the number. Carry. So there's a problem with our tokenizer clearly, because it's not really working correctly. So we can kind of hack it for now by adding spaces. I don't really want to make a real production tokenizer right now. Yeah, so it's left associative the way we implemented it, and that is how it is, I guess. Can we try for fun to change it so it's not left associative? So here we say precedence +1. Just for fun, what happens if we don't say +1 with this expression? Then it becomes right associative. So that's a bit funky. So maybe now we do want like left and right binding power, but we can just say right hand side is an expression and is equal to if operand is equal to carry, then we do this. That's not how you do it. Can I do this like in Rust? Probably not. So let's put that back. And then do I need like this? And then we can say break right hand side. Is that allowed? It does seem to be allowed. Apparently it's not. Okay, so you cannot have a label here. Okay, let's look in the documentation. If I can assign to if statements. So result equals something. You cannot do it inline or what? Is that the only way? Okay, but at least you can do it like that. So why don't we just do it like that? So we need to do this and this. It's a rather long expression. Maybe let's do it another way. So active precedence. Let's just call it that for now. So if the operator is the array, then it's this. Yeah. And then go to else. Okay, so this is effectively the same, but probably a bit easier to read. So we have now, instead of just precedence, we have an active precedence where we handle this special case. It would be nicer if it's just like something you get out up here, but we can change that later. This is just kind of to demonstrate that we can, like, how do we control left and right associativity. So now we can do this, and if we add one, it becomes left associative. Yeah, so that's pretty nice. Let's go back. So we can also control that in our code. Let's add unary minus, which binds tighter than binary arithmetic operators, but less tight than composition. This requires changes to how we start our loop, as we no longer can assume that the first token is an atom, and we need to handle minus as well. But let the types drive us. First, we start with binding power, as this is a unary operator. We only have right binding power, so let's just code this. Okay. I won't really look at the code, but let's go ahead and go into parse expression. And before we return an error, but now we can do the following. So let's get the operator out. And if the operator is not equal to minus, then we'll throw an error still. But otherwise, we can say, and we have to label this. We can say break from up, and we have to return some kind of expression, isn't it? Isn't this is an expression? Just let me put it here for my own sake. And we can't really do that. So that means we cannot make an expression out of a single operator. So that means we have to like get the next thing as well. And we have to think about what is the binding power of the unary, like what is the precedence of the unary minus. So unary precedence. Can we just say like it's where should we put that? Is the real question. I'm going to make a couple of comments. So this should be encoded in the enum definition or in a related table. And it's the same. Sorry, it's the same for this one. So here we can say it's it's int from enum. It's not going to be minus, it's going to be carré, and then we'll say it's 1 less than that. All right, and then we say that the left-hand side, whatever, is something where we pass an expression using the Alexa with this precedence, and of course we give the allocator, and then the result here that we return is a new thing. It's a new thing that we call unary up, so that it has a struct, sorry, and it has a, right now there's only one allowed, but still we'll put that there. And where were we? We were kind of getting lost. Okay, so we were here. So we gotta return a, let's create one of those. Then we assign to it with this weird syntax, and we say it's a unary operation. It has this operator and this operand, and then we return that. So let's see if it compiles, and it does not compile. Right, because I added some new things. Okay, so here unary up. We're just gonna de-init the operand. And let's see if there's another error. There's another error at 131, which is the print. And that should also be kind of simple. I'm also going to print these brackets so we can see with 100% certainty what the precedence is. And now we have this thing. So what happens if we put a minus? It should calculate the minus last, I think. So let's try that. Sorry, put the minus like on the outside. Not sure how to phrase that. Okay, so unexpected character in the number, which is fine, because then we simply have to check whether it's negative first. So we have the string. So if string 0 equals minus, then we have here is negative. We can say that's false. Is negative is true. And then we also need to know where we start from, because now we have to start from 1. Then we have to say, actually, you start from start and you go to the end. And if is negative, we're gonna return minus result. Otherwise, we just return this. And let's try that. So it didn't really work. Variable of type comp time int must be constant comp time. So the result, because we're adding minus now, actually it has to be signed integer. And then let's make this one signed. No, that can still be usize. But the result has to be that. That means basically that all of these we have to change to, let's just do it like this. That should do it. Let's try now. Okay. So how are we supposed to read that? That's kind of interesting. It's a little bit hard to read what exactly the precedence is. So let's go up to the print. This is a binary operation. Left hand side. It's very strange. So instead of printing just doing it like this, calling the print function, why don't we try to print it using the built-in debug thing? Expression, and let's see what happens. Okay, so we have the carry, which is the outermost, and its operand is -2, and then there's some stuff. So that actually is not quite how I wanted it to work. So it's kind of bizarre because it should have passed it. Let's try with -2. It still ends up doing that. Thing is, I'm kind of expecting this call to eat everything. So let's try to debug print this unary operand, and we can do this, and then we can say left hand side print. And what happened to that? It's like we don't even reach this branch for some reason. No. Interesting. Okay, so let's maybe try to print the tokens. So the problem is we tokenize it as one thing. Right, so it's a problem with the tokenizer. And then that means this thing that we set to -2, we don't have to set it to -2. And we can go in and try to fix the tokenizer. Okay, so here we call new on the tokenizer, and we'll see. Okay, it's a minus, so we start collecting the token. And right, so we have this issue that the tokenizer is not really correct. So we kind of have to write it like this. And now we see it works correctly. And then the hello we can get rid of. There was another hello. This one we can get rid of. So now you can see the minus is kind of the outermost thing, the last thing that's computed, which is correct for this expression. But if we did like this, it should be the second thing. So it should be kind of like a -2 times 3. Put a minus here. So something like that. Let's see if that happens. And indeed it happened. So that's great. So, modular the tokenizer is not very good. We can also handle now unary operators. So not It's not so bad. I mean, so what's happening is that this parse expression is kind of starting to get a lot of branches to handle all the different cases. Whereas in the recursive descent parser, it's very, very simple in a way once you have the grammar, I think. But whatever. So prefix binding power, plugging this in, we get some to do, and then he passes that, which is fine, and here this is all good. I mean, to be fair, it was quite easy to implement this. We didn't really have to do a lot of things, and maybe if you do these kind of refactorings of the language where you add a new operator, it's much more easy in Pratt parsing. So kind of incremental development of a language might be a lot easier. And there's something to be said for that. The operand consists of operators bind together. We just function. So now he wants to add postfix operators. Okay, let's try that. That sounds kind of interesting. So postfix, I probably want that to bind tighter than plus and minus and star and slash and carré. So we're gonna put bang here for this factorial operator, and then we can do this, and this is all good. This one we need something. I like that. And this should all be good. It's also a unary operator, so we don't really have to change the expression type, but we do have to change the parser, of course. So how would it work? Well, we get some expression, the first expression, then we check the operator. And this might just work. Well, not really, because here we make a binary operation, so of course that's not gonna work. So how about we say else if operator equals optype.bang, then we try to handle that on its own. So basically like this, I guess. We make a new result. We say it's a unary operator. The operator is this, and the operand it's called now is that. And then we return. So let's try that. I think it might work. So now we have to be careful to put a space, otherwise everything will break because the tokenizer is bad. And it's kind of written in a weird way, but it is correct. It calculates 3 factorial first and then multiplies 2. So that was also easy. But again, it's like one more if statement. Maybe it's okay. So wait, something's wrong here. After we pass the prefix expression, we can see either a postfix or an infix operator, but we bail on recognized operators, which is not going to work. So let's make postfix binding power return an option for the case where the operator is not postfix. Okay. Yeah, so basically, maybe to really do this in a general way, this is like check check if the operator is a postfix operator, instead of having a bunch of if statements where you check on different types or whatever. You probably put those checks into a function. Still have them, but they're in a function, so we forget about it. Continue, and we don't have continue, but we have this if else, so that's probably good. Enough. Postfix binding power, whatever. Do an old test fast. Now we're ready to add a new kind of expression, parenthesize the expressions. Okay, this one thing could be interesting. It is actually not that hard. Okay, we could have done it from the start, but it makes sense to handle it here. You'll see in a moment why. They are just primary expressions. So unfortunately the functions fail. It's kind of an operator, apparently, and it will have the very highest precedence because nothing can, like, everything should stop when it reaches that. So let's try that. Let's try it. We put it here on a separate line because it's special, and it doesn't really make sense to print that, but we'll do it anyway. Token doesn't change. This thing changes, I guess. So maybe we want, we'll just, yeah, let's distinguish to keep the possibility of catching, like, if you have something like this. So we need to, oh, sorry about that. We need to distinguish between left and right facing parentheses. So we'll do that. Left paren, right paren, and down here we'll say else if that stuff, and this is the same. It's actually not going to give a new expression. It's just going to be a way of changing the way things are passed, if that makes sense. So basically, let's see what happens down here. So if the operator is a left paren, it cannot be a left paren. We cannot have a left paren in this position, right? This has to be an operator. So that doesn't really matter. But we can have a left paren in the start of an expression. So we actually have to change this a bit. Now this is going to be kind of an else thing, and no, that one we don't need. And this is if operator is upside minus, we do that, and this is an else, so it doesn't have a condition. And here else if we have left paren, then the first expression is whatever is inside that. So basically we have to say, we already ate it, so that doesn't matter. So let's say inside is an expression which we pass, and here we're gonna eat as much as possible. So it's gonna be 0. but how does it know to stop? So actually the right paren should be of the very lowest precedence, so that everything stops when it reaches that. Let's say maybe this should have the lowest precedence, so all parsing stuff reaches this. That's one way to do it. And how do we do this if it's less than? So we cannot just set it to 0. Well, maybe we can. Let's try it. Let's try it and put it here like that. And no, because then we have to change all of these to 1, which is kind of annoying. But okay. Maybe there's a nicer way we can do that. So parse expression. This one has to be a 1. Okay, I think that was all of them. So we pass whatever's inside, and then we don't really have an expect function, right? If we go look in the Lexa, no, but we can say if Lexa next is not equal to right paren, we return error. Otherwise, we return this expression here. So let's see if it compiles. And it does not compile. And that is because the Lexa, what is it complaining about? Expected type token found up type. So what does this thing return? It returns a token, so I have to say token dot up operator. Not this one, but next. No, that's not. I'm sure that's not how you. Oh, okay, that was how you did. Okay, so now perhaps we can pass parentheses. Then it should just work if we do this. And that kind of worked. What if we add some more stuff on the end? And that also worked. So it's pretty nice. And again, it wasn't really that hard, I guess. You have to kind of really think about this precedence thing of the different operators, and things like parentheses are apparently, it's nice to think of those as operators in this type of parsing. So that's very interesting. So he has some stuff about his stuff failing, which ours might as well. If we try the same expression that he has, like this one. And yeah, it failed. So unexpected character in the number, right? So one reason it fails is because our tokenizer is not very good. So we have to do it like that. But this works no problem. Our tokenizer doesn't have this problem. Pretty nice. Now let's add array indexing operator. Okay. We have array indexing. the ultimate boss of all operators, the ternary. And the thing is almost done. Okay. So what do we have left? Let's go in and look at the to-do. Array indexing. Okay, to-do. We could try to add function calls. But what was the other thing he did? It was ternary operator. It's more tricky, right? Because it has 3 things. So I'm not sure how we will model that. But also I'm thinking about statements. For example, function definition. And maybe that should be a separate thing, because here we are. This is very good for parsing expressions. And maybe like we should keep statements as a separate thing. But I think we'll do that in the next video. So until then, bye bye.